All right, so this final part of the Calc 2.2 notes is a very useful physics application of derivatives. And because derivatives tell us a rate of change at a specific point, it's very useful in finding the instantaneous velocity of an object in motion. So that's not something we've been able to figure out in terms of the exact velocity at any point in time of an object in motion. So we're going to start with this position function here, and this should look familiar. So S of t equals 1/2 gt squared plus v naught. That's the one change that we didn't use this exact equation when we were doing projectile motion, but we did use a variant of this equation, and we're going to come back to it now. This is nothing you need to memorize. Remember, here's gravity, -32 or -9.8, depending if you're in feet or meters. So this position function tells us how far from the ground an object in motion is, assuming that object was traveling vertically. So something shot up vertically into the air or something being dropped from a higher position. So this is for an object in moving in a straight line or vertically. Okay. Okay, so this position function here, S of t, again, tells us where the position, meaning where that object is. So average velocity between 2 points, and I'm going to add that phrase, between 2 points. Average velocity between 2 points. That's just a fancy way of saying slope. So I'm just going to put an M right here to remind us that average velocity, which is how quickly an object's rate of change is moving, is simply slope between 2 points. So we already know how to determine the change in distance divided by change in time. With this we have change in s, which is our change in y. I'm just going to write it as change in y as well so that it looks more familiar. Divided by the change in x. In this case, our x is time. So this is where we usually saw an x, and now we just have a t for time. So this is just another way of saying the slope. When we're talking about how is something changing in velocity between 2 points, we already have a way to do that. That's just slope. But when you get to instantaneous velocity, anything in motion, its position function is it's a curve. So with instantaneous velocity, we're talking about slope of a curve, which is always changing, which takes us back to the idea of a derivative, which we see the limit definition of a derivative here. So instantaneous velocity of a function is that slope that's ever changing, which is just the first derivative. So here, right here, I'm going to highlight kind of the main stuff. I know there's a lot of text right here. So I'm going to this is our position function, S of t. So this is position, meaning where is the object? And that's always determined by S of t. I'm going to use green here to kind of summarize as we go. S of t, where is the object? Velocity, instantaneous velocity right here. How quickly is the object moving at any specific second in time? That's simply the rate of change of the position function, which is the derivative, S prime of t. So S prime of t is instantaneous velocity. I'm highlighting this in green because it's related to our position function. And then if I know the rate of change at an exact point, then if I want to find the speed, that's simply going to be the absolute value of the velocity. So let me specify velocity. Velocity indicates a speed and a direction, meaning if your velocity is -10 with some units, that means the object is traveling in a negative direction, meaning down. If the speed is +10, then it's traveling up. So with speed, it's not asking about direction. It just wants to know how fast the object is traveling. So that's just the absolute value of the velocity. So the absolute value of the derivative of the position function. So right now we have a position function that tells us where an object is. Average velocity between 2 points, that's just our good old slope formula. Instantaneous velocity, this is the extension here that we're using from derivatives. Instantaneous velocity is the instantaneous rate of change, which is the derivative of the position function. So I'm going to use this. This is kind of, okay. And then we have speed, which again is saying, I don't care about the direction, I just want to know how fast the object is moving. So that's just saying take the absolute value of it. Acceleration, so this is the final thing, and acceleration is how quickly the object in motion is speeding up or slowing down. And that's the rate of change of velocity. So we're kind of like going, I don't know if you guys have seen the movie, oh gosh, what's that called? Inception, the dream within the dream. So we're talking about a derivative within a derivative. So when we take the first derivative, we got the velocity. But if we want to know the rate of change of velocity, that is acceleration. So that would be what we call this second derivative. So that would be s double prime is what we would say of t. And that means take the derivative 2 times. So I'm going to draw these arrows here. We have the original position function right here. If I want to know the instantaneous rate of change, that's the velocity, I take the first derivative. If I want to know the rate of change of that velocity, which would tell me the acceleration, that would be the second derivative. So we have these derivatives within derivatives, and we could even go into higher order derivatives, which we will later on in this chapter, but for the sake of these physics problems, we're just going to be moving up to the second derivative, which tells us acceleration. So I know there's a lot of stuff right here in this top half of this page. The important thing to know is this derivative is instantaneous velocity, second derivative is acceleration. And then we have speed here, which again is just the absolute value of the velocity. Okay, so now that we've kind of talked through this stuff, let's apply it to a problem. And we're going to look back up here at this top half to help us out. So a rocket is propelled vertically into the air from a height of 20 feet with an initial velocity of 480 feet per second. So that's all the information we need, which gives us this position function, which would tell us how high the rocket is in the air after any amount of time. If gravity is considered to be constant, then its height in feet after t seconds is given by this equation. So that's just rewording what I just said. First of all, we want to know how high does the rocket go? Now that we have calculus, the knowledge of derivatives and what those mean, we can answer what is that maximum height because we know something about what's going to happen at the maximum height. So I'm going to draw a quick sketch of the position of this rocket, its height based on its time. I'm going to do it out here. So this is the independent variable time, and then we have height. And I'm not even going to label values or units on here. I just want you to visualize over time what this rocket is doing. So the rocket starts at the ground level, at an initial height of 20 feet. It's shot into the air vertically, so as time passes, its height grows higher. At some point, that rocket is going to turn and come back down and hit the ground. So this question is asking, how high does the rocket go? We want to know, what is this point here? Now, we are not using a calculator for this, and that's the big difference. I know you could all grab your graphing calculator. You could plug this in. You could use your max function to find that x and y value right there. But now this derivative, the concept allows us to answer this without graphing it at all. So we know something about the slope, the instantaneous rate of change right here at the top. And that is that tangent line, the slope of the tangent line, which is derivative, is horizontal right there. The slope of that tangent line, the derivative is horizontal, which means that the derivative would have to be 0 at that point. So what that's saying, when it's saying how high does the rocket go, what we're actually going to do to find that out is find out when does that slope of the tangent line, aka derivative, when does s prime of t equal 0? And that is going to give us the time at which this rocket is at its highest point. So we will be able to find the time t that it's at its highest point and then plug it back into the function and see how high it goes. Okay, so we first need to find the derivative and then we'll set it equal to 0. Using our power rule is going to make finding this derivative very easy. So s prime of t, the derivative, I'm going to bring down the 2 multiplied by negative 16. I get negative 32t plus 480. And that's it. That's the derivative. So when does that equal 0? That's a very simple linear equation to solve. We subtract 480, so I've got negative 32t equals negative 480. Divide both sides by negative 32, and we get exactly 15 seconds. So after 15 seconds, so over here, 15 seconds is when that rocket is at its highest point. So when I want to answer how high, I just plug that back into the position function because that is going to tell me how high it is. So s of 15. So you would just plug that in, plug 15 in for t in both of those spots, and we would get that maximum height of 3,620 feet. And we did that without graphing it. So that's the beauty of derivatives. They just kind of open up possibilities of solving problems where you don't need to rely on a graph anymore. So I drew this sketch, but we could have done this without that sketch. Okay, part B is asking how fast is the rocket traveling after 3 seconds. So what this is asking for is the speed. How fast it's moving is speed. So we are asked to find speed at 3 seconds. So this is going to come from that instantaneous rate of change at 3 seconds. Instantaneous rate of change of an object. That's the velocity, and that would be the derivative. So we want to know, we have the derivative right here. So we know that s prime of t, we already did this, is negative 32t plus 480. So when we're being asked to find the speed after 3 seconds, remember speed is just the absolute value of that velocity. We're just going to plug 3 in and solve. So this is going to be the absolute value of negative 32 times 3 plus 480. So this gives us the absolute value of negative 96 plus 480, which is positive 384. Okay, so this means at 3 seconds, this rocket is moving 384 feet per second. So this is interesting because, again, that speed is going to change from second to second. So we know 3 seconds into it, we know the exact speed of that, which would mean, let's say 3 seconds was right here. Then that slope of that tangent line is 384. So it's a very steep, high slope for that, the motion of that rocket. The acceleration, part C, what is the acceleration of that rocket at 3 seconds? So acceleration is, remember, the rate of change of the velocity. So rate of change of the velocity, but remember velocity is the derivative. So we're talking about the derivative of the derivative, or the second derivative. I'm going to go back up here to what we wrote with acceleration right here. So the derivative of the velocity, or the second derivative of the position function. So before we move on, I'm going to recap again. I know this is a lot, and so I like to just review. Position function, s of t. Velocity, s prime of t. Rate of change of the position. Acceleration, I'm going to write, hold on a second. Velocity could be written two ways. It can be written as s prime of t, but we'll also just see it as v of t as well. So velocity. So these two things are the same. S prime of t is the velocity. So you'll see those. That's why I kind of want to review here, because you'll see those interchanged. Acceleration, that can be written two ways. That's the second derivative of the position function, so s double prime of t. Or we can call it the first derivative of the velocity function. So those are the same. So we want to see this kind of relationship. Position function, velocity function, acceleration function. So down here with acceleration, we're being told to find that second derivative of the original position function. So we can find s double prime, here's s first prime right here. And then we would just take the derivative of that. Or we could just take the derivative of velocity. So the s double prime of t, which is the derivative of the velocity function. So here is the derivative of position. The derivative of negative 32t plus 480 is just negative 32. So the acceleration is negative 32 feet per second squared. It's feet per second because we're finding the rate of change of a rate of change. So this is negative 32 feet per second squared every time we talk about acceleration. And that's don't get caught up on the units here. These are great problems for an actual physics class. So those of you who are in AP Physics at all during high school, this will start to look familiar to you guys. Okay, the last one here, part D, how fast was the rocket traveling when it was 1,000 feet in the air? So this is an interesting question because we're asked how fast, which is speed. We are asked how fast, so speed when it's 1,000 feet in the air. This is the first thing we need to answer. So this is kind of our first step. When was it 1,000 feet in the air? And to determine that, we have to set the position function equal to 1,000. So the first thing we need to do is find out when the position was 1,000. So then we're going to use our original position function to find that value of t for when that happened. So negative 16t squared plus 480t plus 20. And let me scoot over. Oops. Okay, so here's my equation. First, step one, we're just finding out when that is going to happen. So first we would subtract 1,000 from both sides, and we end up with negative 16t squared plus 480t minus 980. We need to solve for t to when that whole equation equals 0. For that, we will rely on the quadratic formula. So t will equal opposite b, so negative 480 plus or minus the square root of b squared. So 480 squared minus 4 times a, which is negative 16, times c, which is negative 980. So these are going to be large numbers all over 2a, which is negative 32. So big computations here on the calculator. I would do the inside of that square root first. Okay. So that's going to end up being negative 480 plus or minus. So when I plug the whole square root in, square 480, subtract 4 times negative 16 times negative 980, that's going to end up being a positive. And that ends up being the square root of, or no, after you take the square root, you get 409. 0.487 all over negative 32. So this is going to give us our two possible times. So what that's saying is when we do the negative 480 plus 409.487 divided by negative 32. When we do that, we end up with 2.2 seconds. Or when we do the negative 480 minus 409.487 divided by negative 32, we end up with 27.8 seconds. What does that mean? We have two answers. They both make sense. Well, that just means the rocket is going to be 1,000 feet in the air 2 times. That makes sense, right? Because what comes up must go down. So this is saying there's a rocket, it's in motion, and it's going to equal 1,000 feet. Oops, 1,000 feet right here and right here. So once at 2.2 seconds, once at 27.8 seconds. So the acceleration or the speed, remember we were asked to find the speed when it was that high in the ground. We have two different speeds. Interestingly enough, we will find that those will probably be the same. Okay, so let's go back to what we're being asked here. We're being asked to find the speed, which remember is the absolute value of the velocity, which is just the absolute value of the derivative, s prime. So the derivative we know is negative 32, so s prime of t. We have two things we're finding out now. S prime of 2.2 seconds. And then we're also going to find s prime of 27.8. So that gives us the velocity, and then remember the speed is just the absolute value of that. So I'm going to put my absolute value bars to remind me that that's what I need to do. So we're just going to plug in the values now. We saw above that the derivative was negative 32t. So negative 32 times 2.2 plus 480. And we're taking the absolute value of that. Negative 32 times 2.2 plus 480, that ends up being positive, about positive 409.6, which is 409.6 feet per second. So that is the speed when the rocket is 1,000 feet in the air. At least at the first time it was 1,000 feet in the air. Then the second time it was 1,000 feet in the air was on its way down at 27.8 seconds. So that's going to be negative 32 times 27.8 plus 480, all in this absolute value. That ends up being, when you do negative 32 times 27.8 plus 480, that ends up being negative 409.6. So taking the absolute value, we get the same exact speed both times the rocket is 1,000 feet in the air. Once it was going up, on its way up at 1,000 feet, when that happened, it was traveling at 409.6 feet per second. And on the way down, it was traveling 409 feet per second, which is pretty cool when you think about that. Okay, so I know I went over this first example very slowly and repeated myself a lot. The purpose for doing that is just that this is also new, and I wanted to make sure I covered it slowly. So let's do another example and just to kind of solidify what we're doing here. So in this example number 2 on the last page of this section, we are given the information that a silver dollar is dropped from the top of a building, which is 1,362 feet tall, which, by the way, is close to the height of the Empire State Building. So we're talking about a very tall building. So imagine, people go to the tops of those buildings a lot, and let's see what would happen if someone dropped a silver dollar from the top of one, if you'd want to be underneath that or not. So write the position function for the silver dollar below. So we want to know where the position of that is. Let me just recap from the previous page. Again, you obviously don't need to memorize this, but here's the formula for the position function. 1/2 gt squared plus initial velocity times the time plus initial height. All right, so let's write the position function. S of t equals, negative 1/2. Negative 32 times 1/2, so negative 16t squared plus the initial velocity times time. Let's think about this. You are at the top of a building. You reach your hand out and drop a coin. Think about the initial velocity of that coin, meaning the second when time equals 0. What is the velocity of that coin? And that would be 0. You're not throwing it down. You're not throwing it up. You're just dropping it. So you're not using any force behind it. So that means the initial velocity is just 0. So this whole term right here isn't even a part of this equation. And then initial height, we know the height of the building is 1,362 feet tall, 1,362. So here's our position function, how high the coin is at any given point in time after it's dropped. That means we can find a lot of information actually about that coin. We can figure out how long it takes to get to the ground, how fast it's going when it gets to the ground, how it's changed, what its speed is at any specific point in time. So we'll answer a lot of those questions. Determine the average velocity on the interval 1 to 2. That's meaning from 1 second to 2 seconds, what's the rate of change from that coin? And that's what we're going to figure out. And this first one, between 2 points, this is just the slope. And we know formula for slope is change in y over change in x. So this one is not too difficult, and we're not even going to use the derivative. So change in y is the change in the distance. And change in x, in this case t, is time. So divided by change in time. So we just need to figure out the change in distance from 1 second to 2 seconds. That's going to be s of 2, the position at 2 seconds, minus the position at 1 second, divided by the change in time, so 2 minus 1. So that's going to give us, all you need to do is grab a calculator, plug in 2 to the position function. If I want to know that height at 2 seconds minus the height at 1 second, we're going to plug in 2, so negative 16 times 4 plus 13, 62. I'm going to do that. And that's 1298. That's how high it is at 2 seconds. Minus how high it was at 1 second, which is negative 16 plus 1362. 1346. Divided by change in time, which ends up just being 1. Then we simplify. So 1298 minus 1346, that's going to give us negative 48. Does that make sense? Why is our answer negative? We're talking about velocity between 2 points. Well, think about what direction our coin is traveling. It's going down. Velocity indicates direction and speed, kind of like a vector. So oftentimes we talk about velocity using vectors, which indicate speed and direction. So at between 1 and 2 seconds, that coin's rate of change is average velocity negative 48 feet per second on average between 1 and 2 seconds. 48 feet per second. All right, let's look at B. Determine instantaneous velocity when it's been dropped for 1 second and 2 seconds. So that's 2 different questions. Instantaneous velocity, that's where we're using the derivative. So that would be the derivative function. So let's figure out the derivative of our position function back here. So bring down the 2, multiply it by negative 16. That's negative 32t. And then the derivative of 1362 is just 0. So the derivative of our position function is just negative 32t. So the instantaneous velocity when t equals 1 is just s prime of 1, which is negative 32 feet per second. The instantaneous velocity at 2 seconds is s prime of 2, which is just negative 32 times 2, so negative 64 feet per second. So that's exactly how fast and the direction the coin is moving at 1 second after you drop it, and then at 2 seconds after you drop it. So again, that kind of gives us an idea of acceleration, because look how quickly that is accelerating from negative 32. Just in 1 second, it jumps to negative 64 feet per second. Okay, determine the time required for the coin to reach the ground. This is going to be a two-part problem. Or no, this is not a two-part problem. This is kind of, these next two problems is taking what would have been a two-part problem, which is C and D, and breaking it into these two separate questions. So first of all, let's find out when the coin reaches the ground. So when the coin reaches the ground, that would be when its height is 0. So basically we just want to know, when is that position function equal to 0? In other words, when is negative 16t squared plus 1362 equal to 0? So this is a quadratic equation, but there's only two terms, so we don't really need the quadratic formula. It's a little simpler than that. All we have to do, oops, why do I have, okay, I don't know what these marks are. These are just, ignore those. Negative 16t squared plus 1362. All right, negative 16t squared. So first we subtract 1362 from both sides. Then we can divide by negative 16. And we have t squared equals 85.125. When we take the square root of that to solve and get the time, you get two answers, the positive or negative root of that, which is 9.22. The positive one is the only one that makes sense, so positive 9.22. The reason for that is because the initial height was the height of this building. Think about the curve, the motion of that. So I'm drawing a quick sketch. As time passes, that height goes down. Whoa. So the negative one is that one that doesn't make sense, because we didn't start this coin drop, from the ground level. We started it from up here. So obviously only positive values of time make sense. All right, so that's how long it takes for the coin to reach the ground. You're at the top of the building, you drop the silver dollar. Shortly after 9 seconds later, it's going to hit the ground. Hopefully, not a person, because now we're going to find out how fast that silver dollar is moving when it hits the ground. So anytime you're asked to find impact speed is when that height is 0. Impact speed when the height equals 0, or the position s of t equals 0. Speed of that. Okay, we know speed is the absolute value of the velocity, or absolute value of the derivative. Okay, so we just need to find that, and then we'll know how fast it's moving when it hits the ground, and why that it's a big deal when you drop a coin from the top of a building. So s prime of 9.22. That's going to give us the acceleration, or the velocity, and I need absolute value of that. Found a derivative up top in part B. It's negative 32t. Negative 32 times 9.22. That's going to give us the absolute value of negative 295. So the speed at 9.2 seconds ends up being positive 295.04 feet per second. Think about how fast that coin is moving when it hits the ground. Let's say, roughly the top of the Empire State Building, you drop a coin. When it hits the ground or someone's head, it's going to be moving at 295 feet per second. That is very fast, which is why it can kill someone, which is why you cannot drop coins from the top of buildings. So hopefully next time you're at the top of a tall building and you think about throwing something off of it, you'll remember that it is considered deadly. Okay, so we're going to stop here, and your guys' homework is another worksheet on 2.2, which includes some of these word problems involving something in motion. All right, talk to you next time.